Now I will define what's called a fundamental matrix. Okay, so let me write as a definition. Okay, if x1, okay, t, x and t are linearly independent solutions of the system, let's say x prime equals ax, n by n system, of course, n by n system, then the matrix then the matrix whose columns are xi's is called a fundamental matrix. Okay, so what's a fundamental matrix? It's a matrix of functions, okay, and the columns are just okay, so first column, second column, and the nth column. So this is an n by n matrix. Let's see one example. For example, we solved the system before. Recall that. The solutions of the system. Okay, two solutions of the system. X prime equals şöyle bir matris yapmıştık. 1, 1, 4, 1 x var neydi? İki tane çözüm bulmuştuk. X1 was e üzeri eksi t eksi 2 e üzeri eksi t and x2 were e üzeri 3t 2 e üzeri 3t. Right? Bunu nerede yapmıştık? Ben hemen size söyleyeyim. Bu phase diyagramlarda yaptıydık. İşte bu çözümdü. Okay. X1 bu, X2 de bu. Okay. Yani bu birinci çözümü veren kalım, bu da ikinci çözümü veren kalım. So a fundamental matrix is this then. I take the first column and then the second column. So this is a fundamental matrix. Okay. Okay, well, since these are linearly independent, of course, general solution is just this matrix times C1, C2. Since the columns of a fundamental matrix are linearly independent, uh, the general solution of x prime equals ax is given by xt, a fundamental matrix times C, okay, where C is any n by 1 vector, arbitrary vector. Wronski'nin de bu durumda değil mi? Remark olarak yazayım. Mesela bu örnek için nedir Wronski'nin? For the above example, the Wronskian of the solutions, which solutions? X1 neydi bu? E üzeri eksi t eksi 2 e üzeri eksi t and x2 ikinci çözüm. Bu da e üzeri 3t 2 times e to the power 3t is what? Wronskian bu şeyin determinantı, yani e üzeri eksi t eksi 2 e üzeri eksi t e üzeri 3t 2 çarpı e üzeri 3t, bu da nedir? 2 tane e üzeri 2t, 2t buradan geliyor. 4 tane e üzeri 2t. And this is never zero. It is always positive, right? For all t. Okay. Because our coefficient matrix is constant matrix and it is continuous on the whole real line, therefore the Wronskian has to be, non-negative, sorry, non-zero on the whole real line. And in this case, it is just a positive matrix, a positive function. Okay. Peki. Bir de şey söyleyeyim. Bu fundamental matrislerden bir tanesi özel. The fundamental matrix satisfying the condition that yani en azından constant coefficient'larda bu identity matrizse, identity matrix n by n is called the fundamental matrix. Okay. and there is only one such matrix, and uh, what is that? Well, the general form of the solution was what? E to the power ta times c, right? Uh, and if you see, no, this was the solution. Okey, şöyle diyeyim. Genel çözüm şuydu ya, e üzeri ta çarpı c'ydi. Fundamental matris de nedir? İşte bu c'lere farklı değerler veriyorsunuz. 3 tane çözüm elde ediyorsunuz. Dolayısıyla hani fundamental matrisin kalımları şunlar. E üzeri ta çarpı, buraya bir c1 koyun, c2 koyun, ta çarpı c3, değil mi? 3 tane çözüm. Bunun identity olmasını istiyorsunuz. Ama aslında bakarsanız E üzeri TA matrisi zaten onu sağlıyor. Çünkü T yerine 0 yazarsanız E üzeri 0, o da identity matrisi. Note that e to the power 0 times A, which is what? This is identity plus 0 times A over 1 factorial, 0 squared, A squared, 2 factorial, and so on. This is just the identity matrix, and hence uh, the fundamental matrix. So a fundamental matrix which is identity at 0 is nothing but this gadget. Bunu da şöyle gösteriyor kitap. Ben de onu kullanayım. E üzeri t çarpı a. Okay, so this matrix is called the fundamental matrix of the system. Okay, of the system, constant coefficient system. Okay, pardon. Okay. Okay, so that's it about fundamental matrices. We have now non-homogeneous systems. We will make use of fundamental matrices when we consider now non-homogeneous systems. Non-homogeneous linear systems. Okay, so what's a non-homogeneous linear system? It is something like this. X prime ax plus a non-homogeneous part. Or we write it this way, x prime minus ax. If it were 0, then it would be homogeneous. If it is not 0, then we have a non-homogeneous system. Okay, now we would like to solve this kind of systems and find the general solution. The observation is the following. If we have, let's say, x1 and x2 are two solutions of the system, Ya da şöyle diyeyim. Neyse tamam. Solutions of the system. Then we have what? X1 prime is equal to A times X1 plus G, and X2 prime equals A times X2 plus G, and thus X1 prime minus X2 prime is equal to what? If you subtract these two, G's will be cancelled, and in A parentheses I have here X1 minus X2. Hence X1 minus X2 is a solution of the homogeneous equation. So this means what? This means hence thus x1 t is equal to this. Some solution ya da x2 ile başlayayım. Some solution of the system plus a solution of the homogeneous equation, where, right, xh is a solution şöyle diyeyim, c diye is a solution of the homogeneous system x prime is equal to ax. Okay. And actually, any solution of the equation has this form, because we have no condition on x1 and x2. x1 is a solution of the system, non-homogeneous system. x2 is any other solution of the non-homogeneous system, and we see that in that case this any solution is written as the sum of a particular solution of the system plus a solution of the homogeneous equation. So hence the general solution xg, let's say general, so G stands for the general of the non-homogeneous equation, non-homogeneous system, x prime equals ax plus g, has the form şu şekilde o zaman. Genel çözüm neymiş? Her çözüm, her x2 çözümü bu x1 çözümüne bir tane homojen sistemin bir çözümünü ekleyerek elde ediyorum. Bu seçtiğim x1 çözümüne particular çözüm diyeceğim. Bu homojen sistemin çözümüne de complementary solution diyeceğim. Has this form where xp t is any particular solution of x prime ax plus g, and xc is the general solution of the homogeneous system. Okay, system x prime equals ax ya da şöyle diyeyim equals 0. So the general solution of the non-homogeneous system has two parts. One part is just the general solution of the non-homogeneous, of the homogeneous system, plus a particular solution of the non-homogeneous equation. So to write down the general solution of the non-homogeneous equation, all you need is one particular solution of the non-homogeneous system along with, of course, the general solution of the homogeneous equation. But we already know how to compute, how to obtain the general solution of the homogeneous equation. So to write down xg, we have to find a particular solution. Why I write this C? C stands for the complementary solution. In this case, xc will be called the complementary solution. Okay, it is the general solution of the homogeneous equation. So we have to find then this particular solution. So how to obtain a particular solution? X P T of the system. X prime equals AX plus G. Okay. There are, I guess, like 4 different methods in the book. I will only give okay, one of them because it works for all of them. One of them is called diagonalization, but it works only for systems which are diagonalizable. And then there is one method called undetermined coefficients, but this is something we have to see first for ordinary equations, so I will skip also that one. And there is one using Laplace transform, but we haven't seen Laplace transform yet either. So I will give only the variation of parameters, which works for all of them. So that will be actually enough for our purposes. A method to obtain a particular solution is so-called variation of parameters. Okay, now let me explain what this is. Remember that, so recall that the solution of this, right, if it were homogeneous, what would be the solution? So it is just xt is e to the power tc, no, ta times c. This is the fundamental matrix, but actually you don't have to find the fundamental matrix. You can obtain just one solution. Okay, one set of solutions, linearly independent solutions, and multiply this by C. Not necessarily the fundamental matrix. You can use any fundamental matrix. Where isterseniz şunu şöyle yazayım. Okay. Where is the fundamental matrix? Of course, one can choose this thing to be just e to the power ta, but sometimes it is easier to obtain just a fundamental matrix, okay? Because to obtain this one, you may have to do some extra computations, and we don't need it, okay? All we need is one fundamental matrix. All right. So solution of this homogeneous system has this form, right? We know this. What about solutions of non-homogeneous equations? For the non-homogeneous equation system, x prime equals ax plus g, we try functions of the form like this: xt, fundamental matrix alıyoruz. Here for the homogeneous equation we had an arbitrary vector, right? Arbitrary vector. Instead of this arbitrary vector, let's put an arbitrary function. I mean vector valued function, of course, ut. Okay. To obtain a solution of the non-homogeneous equation, where ut is a arbitrary is a suitable vector valued function. So what we do, instead of C, we use a vector of functions, right? C was a bunch of real numbers. Now I use bunch of functions, okay? And this is the reason why we call this method variation of parameters. These CIs are parameters, and we replace them by functions. We, in other words, let those parameters change in time, okay, so that they become functions. We let them vary with time. That's why, this method is called variation of parameters. So these are not just constant numbers anymore. They are just continuously changing parameters. Okay. So we hope that this gadget will be a solution of the non-homogeneous equation. So to obtain ya da to see whether such ut exists or not, let's plug xt into the equation. X prime equals ax plus g. So I have to take the derivative of this x prime. So x prime is equal to what? X prime is just, since these are functions of t in the product form, their derivatives obey Leibniz rule. So derivative of the first function plus the second plus the first function times the derivative of the second. And let's plug them into the equation. So we get what? X prime. So psi times u plus psi prime, and then psi times uh, u prime, a times psi, so a times x is just psi times u plus g. So from this we get what? A times psi times u plus g. So here I have this gadget. But what is this gadget? So note that, uh, so a times psi. What is this? Well, remember that these are solutions of the homogeneous equation. Actually, the columns of this are the solutions of the homogeneous equation, right? x1, x2, xn, right? Where x i's are solutions of the homogeneous equation. What was that? Homogeneous equation. X prime equals a times x. Therefore, hence, hence a times x I is equal to x I prime for all I from 1 up to n. For all I from 1 up to n. Right? So, hence, a times psi is just what? What is this? This is just a times the first column, a times the second column. So the columns of this product are just these. But you know what is this? This is just the first derivative of the first solution. This is the derivative of the second solution, and this is the derivative of the nth solution. And what is this? Well, this is nothing but just the derivative of the fundamental solution, right? So this is just phi prime. Phi is just these vectors without primes. So when I take the derivatives, I get phi prime. Now let's go back to the equation. Now I have a times phi, so this will be phi prime. So we get what? Back to the equation. Ne vardı elimizde? Psi prime u. Okay. Psi prime u. Psi u prime equals okay, a times psi u plus g. But a times psi is just psi prime u plus g, right? Okay. Here is this. And here, now I can cancel these two terms. So, and we get what? Just G. Okay. Well, from this we see what? We see that U prime is just this matrix of solutions, but they form a non so it was an invertible matrix, right? The determinant was the Wronskian, and Wronskian is never zero. So this function is invertible at all for all t. So there's no harm writing it this way. I take inverse and put it here. From this we get ut, u which is ut, just integral of, okay, this gadget. And once we have, of course, this, hence x of g would be not x of g. I was looking for a particular solution. So particular solution will be what? Neydi çözümümüz? Fundamental solution çarpı ut idi. Dolayısıyla bir tane fundamental solution alacağım. Bunu ut ile çarpacağım. Yani fundamental solution çarpı inverse of the fundamental matrix gt dt. So particular solution is obtained this way. Okay. Well, next time I'll do some examples related to this. I don't have much time, but let me just make the following remark. This is not actually something, you know, surprising. I mean, we have seen this method before. Remember, to solve this ordinary equation, let's say, okay, what was P, ordinary first order equation, we used integrating factors, right? We multiplied both sides with this. Okay. And then, okay, so what was this? This was d over dt, e to the power pt dt, y equals e to the power, or, okay, qt times e to the power pt dt. And then we integrate this one more time and we obtain the solution as e to the power minus pt dt times integral, right? I first integrate and then divide by this. So I get this thing, integral of qt times integral e to the power integral of pt dt. And then I have another dt here, right? We just repeat the same thing to systems. So for systems, I have x prime minus ax equals gt, right? So my function P is minus A and Q is G, right? So P is minus A, constant matrix, and Q is this function GT. So if I do the same thing, my integrating factor will be what? E to the power pt dt. So it is just e to the power uh, minus a dt. A is a constant matrix, So its integral will be just t times a. So this is e to the power ta. So this is my integrating factor, and what I do, I multiply my equation with this, and we obtain what? We will obtain something like this. So e to the power ta times x and equals e to the power minus ta gt. And then you integrate both sides. So you get e to the power minus ta x is equal to integral of e to the power minus ta gt dt. And from this we get x equals e to the power ta times e to the power ta gt dt. Well, you see that I have e to the power ta. E to the power ta is the fundamental matrix, but also it is the fundamental matrix, but it's also a fundamental matrix. So if I plug this into this formula, so I would get xt e to the power ta. So I have the fundamental matrix times e to the power minus ta. Well, that's the inverse of the fundamental matrix. So, sorry. Inverse of the fundamental matrix times gt dt. So this variation of parameters actually is something new. It is just our old integrating factor method to find a solution. Değil mi? Aynı şeyi bulduk burada da. Okay. Let me stop here.